Continuing our discussion of Lecture 15x, page 2 for descriptive inorganic chemistry, we're looking at the last compound on the page, which is a nonmetal oxide. So what's the pattern with nonmetal oxides? And in this particular case, I chose dichlorine heptoxide, which has peculiar behavior. Sometimes you'll not be able to predict this, but based on nonmetal oxides, we previously suggested that nonmetal oxides give us acidic solutions, i.e. pH is less than 7. Is that always true for all nonmetal oxides to the right of the staircase or metalloid staircase? No, but let's see what happens in this particular case. So dichlorine, heptoxide, it's a gas, which was interesting to figure out. And let's look at its dissolution process. We can go to being aquated, surrounded by water molecules. We don't know much about the equilibrium. We could probably use thermodynamics to calculate, in this particular case, how extensive, whether the reaction goes to the right or left, depending on the delta G, but that's a previous exercise. So that's my dissolution process. 1. Ooh, sneaky here. So part of the dissolution process we're going to suggest as the aquated form reacts with the water molecule and will recreate. Well, what we suggested in a previous exercise, and probably from refreshment experience, we're just going to add the water molecule. Let's see what we get. So we got 2 hydrogens. I'll put them in that order. Chlorines typically next, and I'll put the oxygens in the outer side. So now I got a species that's H2ClO8. What does that kind of remind me of? Well, if this acts like an acid, is that a common acid? That looks like maybe it's polymeric. Hey, let's look at its empirical formula. So let's look at that. Right? Do a little thinking. Oh, hey, oh my gosh, what is that? That's perchloric acid. So we actually get 2 perchloric acids. Sneaky. Does it always happen? No, but don't be surprised if other nonmetal oxides have that similar or like behavior. Or later on, we'll talk about disproportionation, other topic based on today's activities. Oh, if we look at the Ka for perchloric acid, we model it as 10 to the 4th. If you look at Weller's book, the Ka is modeled as 10 to the 11th, which is the second highest, strongest common acid. Hydroiodic is stronger, so it's listed, but we use the Ka 10 to the 4th because we're suggesting that all these strong acids are leveled to the hydronium ion in solution, which we could model next. But I think, yeah, we could do that real quick. So we're suggesting that perchloric acid, strong acid, 100%. My Ka is 10 to the 4th is what we're suggesting based on leveling. And that way we get hydrogen ion plus the perchlorate ion. A little review of nomenclature. Some people get thrown by that. Some people have asked me to do that in this class because of the wide background we have, wide range of backgrounds. That's okay. Keep on asking good questions like that. Now, perchlorate ion, since this is a strong acid, very, very strong acid, then that means, and that's my acid, that's my strongest acid I could have in solution in an aqueous system based on previous discussion, based on the leveling effect, and this guy must be a very, very weak base. It's one of my spectator ions that we listed previously. And there was a periodic pattern that we showed previously, so you might take a look at that. I also put a freshman's handout up that talks about calculating the KBs and KAs for these spectator ions. You may take a look at that.